Dear students, welcome to the lecture number 7. So today in this talk we shall see few more results on normal topological space and we will close this chapter. So let's start with the theorem that is every matrizable space is normal. That's mean we have been given one topological space X which is matrizable, or you can assume that D is a metric on X, and then we need to show that X is normal. That's mean we need to check two properties, right? One is any one point set is closed, and another property is if we choose two disjoint closed sets, suppose A and B, then there exist two disjoint open sets U and V. One contains A and another contains B, right? So here is the proof. So let X be a topological space, or you can just write matrizable space. With the metric D. Now it is easy to check that any singleton set is closed, right? Because any matrizable space is Hausdorff, or you can just directly prove it. That proof is very simple. Now we need to check the second property, that is let A and B be two closed sets in X, and we need to find two disjoint open sets containing them, right? So first of all, let say A belongs to A, that is small a, be an arbitrary elements of capital A. Now that implies A does not belong to B, right? Why? Because A intersection B is empty, right? Now that implies A belongs to B complement, that is X minus B, right? Now B is an open set. Sorry, B is an closed set, so this is an open set, right? Now since X minus B is an open set, so there exists an epsilon, say epsilon A bigger than 0, such that A belongs to this ball, say B, here it is D, A comma epsilon A, that is the ball with centered at A and with radius epsilon A, and D means the metric is D, that is subset of X minus B, right? Now that will imply this ball does not intersect B, right? And for each set A we can get this kind of ball. Now similarly, or we can write So for each B again, belongs to B, we know that B belongs to x minus A. Therefore, there exists an epsilon say B bigger than 0 such that B belongs to that ball B epsilon B, which is subset of x minus A. Right? Now that will imply the ball B comma epsilon B intersect A is empty. Right? Now we note that, so what is the situation? Now this is my A and this is my B. Right? Now what we are doing, for each point in A, we are taking one this kind of ball which is different from, that is, which is disjoint from B. Now similarly for each point we get this kind of ball. Right? And this covers A. Similarly for B, again we get this kind of ball. Right? Which covers B. Now note that if we assume, so suppose let U equal to that union, say union of A belongs to A, this B, D, A comma epsilon A, and if we write V equal to union of B belongs to B, that ball, if we choose this, then U intersection V may not be empty because it can be in this, right? There might be some intersection. Right? So this is a problem. So what we will do, what we will choose this, how do we choose this kind of open set? Now just we have to apply one trick. So instead of this epsilon by epsilon A, we will choose epsilon A by 2. Then it will work. Okay, let's see how it will work. So we will choose, this is my epsilon A by 2, this is epsilon B by 2. Then obviously, then U is an open set containing A, and V is an open set containing B. So this is clear, right? Now we need to check that only U intersection V is empty. Now we claim so U intersection V is empty. Why this is empty? Now if possible, there is a Z belongs to U intersection V. That's mean Z belongs to U and Z belongs to V, right? Now that implies there exists A belongs to A and B belongs to B such that your that my Z belongs to the ball with f z by 2 and again Z belongs to this ball. Right? Now this will imply the distance between A comma Z is less than or equal to epsilon A by 2 and distance between B comma Z is less than or equal to epsilon b by 2. Now that will imply what is my d of a comma b. Now that is less than equal to d of a comma z plus distance between b and z, and this is less than equal to epsilon a plus epsilon b by 2. Right? Now we have two possibilities between epsilon a and epsilon b. Now if epsilon a less than equal to epsilon b, now that will imply d of a b less than equal to epsilon b. Right? Now this will imply b belongs to, say a belongs to the ball of radius epsilon b with centered at v. Right? And this is a contradiction. This contradicts the fact that BD B epsilon B intersect A is empty. Right? So we choose ball in this way. We can see that one. See? Right? So we get a contradiction. Now there is another possibility. If now say epsilon b less than equal to epsilon a. Now that will imply d of a comma b, which is less than equal to epsilon a plus epsilon b by 2, that will be less than equal to epsilon a. Now then we can say b belongs to the ball of centered A and radius epsilon A. Now that imply, or you can say directly, so this is a contradiction as this contradicts the fact that the ball intersect V is empty. Right? So we get a contradiction for each of these two cases. Now that will imply U intersection V must be empty, and thus X is normal. Now we shall prove another result, or you can say the final result of this chapter. It says every compact Hausdorff space is normal. Here is the theorem. So every compact Hausdorff space is normal. Proof. So suppose it is given that X is a compact Hausdorff topological space, and we need to prove that that is normal. That means we need to check two properties, right? So first of all, that one, that the singleton points are closed. Now this property is trivial. Why this is trivial? Because it is already given that the topological space is Hausdorff. Now since it is Hausdorff, so we can prove that singleton sets are closed, right? So that property is trivial. Now we need to check only the second property, that is for any two disjoint closed sets, we will have two disjoint open sets containing them, right? But there are two steps for this theorem. So for the first step, or in the first step, we shall prove that the topological space is regular and then in the next step we shall prove that the topological space is normal. So there are two steps. So first of all, we assume that, so let X be a compact Hausdorff topological space. Now since X is Hausdorff, so we can say that singleton sets or one point sets are closed in X. Right? Now we first prove that, so in the first step we prove that X is regular. So first of all, step 1. So X is regular. And using the fact that X is regular, we will prove that X is normal. Okay, so for that we choose 2 points. So let X be a point in X and B be a closed set in X such that X does not belong to B. Fine. Now it is given that X is Hausdorff, that is the topological space is Hausdorff, right? That implies for each point B belongs to that my set V, there exist open sets, say UB and VB such that X belongs to UB and B belongs to VB. So such that X belongs to UB and B belongs to VB. Now here note that I am writing here X belongs to UB, that is I denoted that open set by UB, not by UX. Just to remember that, but this is not a mistake actually. So I am not writing UX. Why I am writing UB, we will see this later. Okay, so this is not a mistake. Anyway, such that this and UB intersection VB is empty, right? Because they are Hausdorff. Now, if we take the collection all such VB where B belongs to the set B is an open cover of B, right? Why this is an open cover? Obviously this is covers B and each VB is an open set, so this collection is an open cover of B. Now can we say that it has a finite subcover? So in particular we cannot, because the subset of a compact set may not be a subset, may not be a compact set, right? But here B is a compact set. Why? Because B is closed. Now since X is compact and B is closed in X, therefore B is also compact. Now we can say that this collection has a finite subcover. Now that implies, so there exists B1, B2 up to Bn, so belongs to B, such that B subset of union of I equal to 1 to n, that V Bi, right? That's when B is subset of this. Now let say Bx equal to that collection. And Ux equal to union of intersection of I equal to 1 to n Ubi, right? Now obviously so B subset of Vx and x belongs to Ux. Why x belongs to Ux? Because x belongs to Ubi for all I, right? For all I. Now that implies x belongs to Ux. Okay. Now we also claim that Vx intersect with Ux is empty. Why this is empty? Now we claim Ux intersect with Vx is empty. Now for an example, so if possible, so Z belongs to Ux intersection Vx. Now that will imply Z belongs to Ux, which is my just intersection of I equal to 1 to n Ubi. That imply Z belongs to so Ubi for all I, right? Also Z belongs to Vx. Now what is my Vx? That is union of I equal to 1 to n Vbi, right? Now that imply there exists J, that is belongs to that set 1 up to n, such that Z belongs to Vbi or Vbj, right? Now that imply Z belongs to Ubj intersect Vbj, and this is a contradiction. What is the contradiction? That Ubj intersection Vbj should be, their intersection should be empty, right? Okay, so that's when we prove that, so we choose one point x and one closed set V which is different, that is which is disjoint from the singleton set x, right? That is x does not belong to B, and we found two open sets, say Ux and Vx, containing them and they are disjoint. That's mean x is regular. X is regular. Now we move to the next section, that is part 2, to prove that x is normal as well. Okay, so that singleton points are closed, that is done, right? Now we need to choose two closed set, two disjoint closed sets, and we need to find, that is we need to prove that they are separated by open sets. That's all. So let A and B be two disjoint closed sets in X, right? Now by part 1, for each A belongs to A, there exist open sets UA and VA such that A belongs to UA and that my B subset of VA and UA intersection VA is empty, right? Which is equivalent to saying that X is regular, right? That's mean one point, that point A and the closed set B are separated by the open sets. Now again, take this collection, this collection, right? Now this collection covers covers A, and also each of UA is open, therefore this is an open cover of A. So we can say that now this is an open cover of A. But again A is compact. Why? Because A is closed. Now A being a closed set in a compact topological space X, so is also compact. So we can just write, since A is a closed set in a compact topological space X, so A is also compact. Now therefore, again, so we just repeat the previous argument. There exist A1, A2, say AM belongs to A, that is a finite collection, such that A is covered by the union I equal to 1 to M A U AI, right? Now let U equal to this union and let V equal to their intersection, that is corresponding VAI. Now since that V subset of VAI for all I equal to 1 to up to N, that imply V subset of V, and it is also a subset of U, right? And claim U intersection V is empty. Now it is also the same argument, right? Now again, let if possible Z belongs to U intersection V. Now then Z belongs to U equal to the union UAI and Z belongs to V intersection I equal to 1 to M VAI, right? Now that imply Z belongs to VAI for all I equal to 1 to up to M. Now that imply since UAI and UAI and VAI are disjoint, so we can say Z does not belong to UAI, as UAI intersection VAI is empty. Now that imply Z does not belong to U. Now this is a contradiction. If you don't like this contradiction, you can give the similar contradiction as in the previous argument, right? So anyway, you can get a contradiction. So therefore, there exist open sets U and V such that A subset of U and V subset of B subset of V and U intersection V are empty. Thus, X is normal. So this completes the proof. The proof is actually simple. It just it can be done by some repeated argument, right? Okay, now this is basically the last important theorem for this chapter. Now we will see some problems for this chapter. Okay. Now, before going to the applications of the above theorems, I want to state few results which will be very useful for these examples. And these are the well-known results actually. So first of all, first result is, say, result 1. So let f be a function from x to y. So it is continuous function. So continuous function, and say xn be a sequence in x such that xn converges to x for some x in x. Say this belongs to x. Then the sequence f of xn is also converts to f of x. Right? Now the proof of this theorem is very simple. If you want to prove, so you can just use the definition of continuity and you will get this result, right? Even you have seen this result in your calculus course as well. So this is the first one result. Another result is, that is very important. This is my result 2. It says, so let A be a dense set in X. Okay. That's mean, so that is, you can say A closure equal to X, right? And let X be an arbitrary element from X. Then, so there exist Xn, all of this Xn belongs to A for all n belongs to natural number such that Xn converges to X. Okay. So this is not true in general, but this is true if the topological space X is first countable. So we have to assume that X be a, so we can write this before, right? So we can write that so let X be a first countable topological space. Okay, why this is true? The proof of this one is also simple, because you can see that, so if the topological space is first countable, then we can choose say beta x equal to say collection of Bn, Ba, so countable basis at x, right? Now choose xn belongs to that Bn. So for all n. Then you can find that if you choose any open set containing x, then that open set should contain some Bn, that's mean should contain some point xn, that's mean xn converts to x. So if x is a first countable topological space and A is a dense subset of x, then for any point in x we always get a sequence in that dense set such that that sequence converts to that point. So this is the result 2. Now we will use these two results to prove our main theorems. Okay. Now before that I want to just state the Eurasian lemma, and I will prove the Eurasian lemma in the next lecture. So let's just write the statement of Eurasian lemma. So I will prove that Eurasian lemma in the next lecture. Okay. So here it is. The Eurasian lemma. This lemma says, so let X be a normal topological space and let A and B be two disjoint closed set in X, then there exists a continuous function f from that topological space X to 0, 1 such that f of A equal to 0 for all A belongs to A, and f of B equal to 1 for all B belongs to B. That's mean if X is a normal topological space and A and B be two disjoint closed sets in X, then we have a continuous function from X to 0, 1 such that f gives the value 0, that is the set A goes to 0 and the set B goes to 1, and but the function will be the continuous function. Okay. Now we will use this 1, 2, 3, these three results, that is the Eurasian lemma and this result 1 and result 2, to prove the theorem, or you can say one example to prove that RL cross RL is not normal. As I told before, the proof of that, that is RL cross RL is not normal, is very difficult one. So we will use these three results. Okay. Anyway, so now I just want to combine the result 1 and result 2, and I want to give another result. Okay, so here is the result 3. So let X be a first countable topological space then any continuous function f from x to y is uniquely determined by its values on a dense set in X. That's mean, so it says, so let f x to y be continuous and A be a dense subset of this y, and so A be a dense subset of x, that is A closure equal to x. Okay, now we claim that f is uniquely determined by its values on A. That's mean if you know the values of f on A, then you know the values of f on x. That's mean you don't have to assume the values of f in x. So it is sufficient to know the values of f in A, right? That's mean it is sufficient to know the values of f on A. Why? Because here is the short proof. So first of all, so let x be an arbitrary point in X, right? And now since X is first countable, so that implies that exists a sequence xn in A such that xn converges to x, right? Now since the function f x to y is continuous, that implies f of xn converts to f of x, right? Now you know the values of f on A. Now since xn belongs to A and f of xn converts to f of x, that implies f is uniquely determined by its values on A, right? For an example, see, So suppose if it's a function from R to R, suppose it is given that f of q, that is f of x equal to 0 for all x belongs to q. Now can you extend the function? Now can you say what is the function if this is continuous? Right? That implies this should be f of x equal to 0 for all x belongs to R. That's mean if f is identically 0 function. Okay, anyway. So now we are ready to prove our main result. That is our main theorem. It says the topological space RL cross RL is not normal. Okay, so here is the proof. So first we recall few properties of RL cross RL. So some properties of RL cross RL. So first one is RL cross RL is first countable. So it is easy to see that it is first countable. Why? Because for any point, say x cross y belongs to R cross R. So here I am writing R cross R because the topological space is R cross R and the topology is given, that lower limit topology in each of the case. So the topological space with the topology is denoted by RL cross RL, right? But the space is R cross R. So for any this point, say this one, say x comma x plus 1 by n product with x, say y comma y plus 1 by n, where n belongs to natural number, forms a countable basis at the point x cross y, right? So it is first countable. Now it is easy to see that RL cross RL has a countable dense subset, that is it is separable. So RL cross RL is separable. That is RL cross RL has a countable dense subset. Now this is also simple. So can you guess one countable dense subset or set in RL cross RL? It is easy to see that so Q cross Q, the set Q cross Q forms a basis, so Q cross Q is a dense set in RL cross RL. Why? So this proof is also simple, right? So first of all, let any point, so x cross y, and choose any open set U, right? So this U is open in RL cross RL, right? Now since it is first countable again, so we can choose one n such that x plus 1 by n, so you can write it is that x comma x plus 1 by n product with y comma y plus 1 by n, that is subset of u, right? Now choose a comma b belongs to q, that is rational number, such that say a less than equal to x less than x plus 1 by n and b less than equal to y less than equal to y plus 1 by n. Now that imply a cross b belongs to q cross q intersection this open set, or you can intersect u, right? So that imply that q cross q is a dense set in RL cross RL. So RL cross RL has a countable dense set. So now we ready to prove the main part, but I want to recall another one, that is recall that the set D, which is just the diagonal, which is anti-diagonal, x comma minus x, x belongs to R, is a discrete set in RL cross RL, right? That's mean it has a discrete topology in RL cross RL. Why? We know that, so this was my anti-diagonal, right? And we know that for any point we have this, which intersect only one point, right? So you can write as for any point x cross minus x, I can write that x cross minus x, right? So x cross minus x. U intersect D is singleton x cross minus x. What is my U? Where U equal to that set, that is x comma x plus 1 by n. So you can just write 1 cross minus x comma minus x plus 1, this one, right? So if we choose my U equal to this, then U intersect D equal to singleton. That's mean any singleton point, right, is a discrete topology in D. Now since D has discrete topology, that's mean any set any subset A in D is closed in D. Right? Further, we have seen that D is closed, right? Because D complement is open. We have seen that. Again, the similar logic. If you choose any point outside D, you can always get a open neighborhood around that point which will not intersect D, right? So further, D is closed in RL cross RL. So D is closed in RL cross RL. We have proved that, and any subset of D is closed in D because D has discrete topology. Therefore, a subset of D is closed in RL cross RL, and this is true for any closed subset of D, right? Therefore, we can say for any subset A, subset of D, so A and D minus A both are subset of D, right? Are disjoint closed sets in RL cross RL, right? Now, if RL cross RL is normal, then we will get a contradiction. Now suppose, if possible, RL cross RL is normal, then by Eurasian lemma we get a continuous function say it is fa from RL cross RL to 0 1, right, such that fa at A is 0, fa at D minus A equal to 1, and the other point it has some values, so it is a continuous function. Why I write here this A? Because this f depends on A, right? So therefore the collection if A, where A subset of D has cardinality. What is the cardinality of this one? It has the same cardinality of the power set of D, right? Because we have that many functions, that is that many different functions, as many as we have the subsets of D. And what is my D? D is just my R, that is, it has the same cardinality of R, right? So it has the cardinality, that power set of R, right? It is clear. So we can write in a different notation, since for any subset of D we get a different function, right? Okay. Now in the other way, we know that Q cross Q is dense in R, RL cross RL, right? Now RL cross RL is the first countable, we have seen that, right? Now since RL cross RL is first countable, so any continuous function if from RL cross RL to 0 1 is uniquely determined by its values on Q cross Q. Therefore, the collection of all continuous functions if that RL cross RL to 0 1 has the same cardinality as the collection of all functions if from Q to Q, Q cross Q to 0 1. Note that here I have written continuous, but here I have written all functions. Why? Because we have seen that here, right? So any continuous function from RL to RL, RL cross RL to 0 1 is uniquely determined by its values on the dense set, right? Q cross Q. Therefore, the collection of all continuous functions from RL cross RL to 0 1 has the same cardinality as the collection of all functions f from Q cross Q to 0 1. Now, what is the cardinality of these functions? So now the cardinality of the collection of all functions if Q cross Q to 0 1 is, so what is the cardinality of this one? It is same as cardinality of 0 1, right? Power cardinality of Q cross Q. This one. Now what is the cardinality of 0 1? It is the same as the cardinality of R, right? Or we can say the cardinality of 2 to the power n. So, but that cardinality of this set 0 1 is same as cardinality of R, right? It is same as 2 to the power natural number n, and Q cross Q is countable, so its cardinality is same as cardinality of n, right? Therefore, cardinality of this set is same as, you can write 2 to the power n, this one again power n, right? So it is same as 2 to the power n, again cardinality of n, again the cardinality of n into cardinality of n is again cardinality of n, right? So equal to again cardinality of R. That is the real line. You can write this R. These are Q. Fine. That's mean the cardinality of this collection of functions, that is all the functions from Q cross Q to 0 1, is just the cardinality of R, right? And this is same as the cardinality of all continuous functions f, which is from RL cross RL to 0 1. But we have already found that the cardinality of all such functions, right, which is a continuous function from RL to RL cross RL to 0, 1 with some extra property has the cardinality of P, that is power set of R. Now this implies, or you can write that, or you can say it is star. Say this is star. But from star we have the cardinality of continuous functions if from RL cross RL to 0, 1 with some extra properties is cardinality of power set of R, right? Now that implies cardinality of power set of R is less than equal to cardinality of R. Why? Because here we get the cardinality of the continuous functions from RL to RL to 0, 1 with some extra properties is this, right? And we have seen that the cardinality of all continuous function from RL cross RL to 0, 1 without any extra properties is cardinality of R. That's mean we have this, but this is a contradiction. Now this is a contradiction. Therefore, RL cross RL is not normal. Now I state the final result of this chapter. It says, so I will not give the complete proof. So it says, so in the previous theorem we have seen that RL cross RL is not normal, but we know that RL is normal, right? That's mean product of two normal spaces may not be normal. Now we prove that the similar result as that subspace of a normal space may not be normal. Now for this we need one result, so which I will not prove because the proof is very difficult. So it is a paper actually. So there was a paper, so you can say article actually. Since it is just result of an article, so it is difficult. So it says if J is uncountable, then Rj, that is that J many products of R is not normal. Anyway, so if you have any interest, so you can ask me, then I will give one lecture on this one, that is R power J is not normal. If you have any interest, so I can give you the proof as well. It is up to you. Okay, so I will use that result, that is R power J is not normal. So first of all, we know that the closed interval 0, 1 power J, so if J is uncountable, is compact, right? We know that is arbitrary product of 0, 1, that is of compact sets is compact. Why? By the Tikhonov theorem, right? by Tikhonov theorem. Right? So now let x equal to that 0, 1, this with product topology. Now then x is compact by that previous Tikhonov theorem, and also x is Hausdorff. Why x is Hausdorff? We have seen that any product of this arbitrary product of Hausdorff spaces is Hausdorff. As product of Hausdorff spaces is Hausdorff. So we have proved that, right? Okay. Now since x is compact and x is Hausdorff, that means x is normal. X is normal. Why x is normal? Again, we have proved this, right? So by a previous result. Right? Now let y equal to that 0, 1 power j. That is countable, that is uncountable product of open interval 0, 1. Now then y is a subspace of x, right? But y is homeomorphic to r power j, which is not normal. Therefore, subspace of a normal space may not be a normal. So this completes the chapter.